Absolutely. We're talking about how elements can fundamentally change just by gaining or losing these tiny things called electrons.
Right. And we've looked at some great material that breaks down this whole process.
Yeah, our goal here is basically to unpack electron transfer, why it happens, what the results are. We want to help you get a really solid handle on these key ideas pretty quickly.
Okay, so let's start at the beginning. Atoms. We know they've got the nucleus, right?
Mm-hmm.
Protons, neutrons, and then electrons whizzing around.
Uh-huh. But it's those outermost electrons, the valence electrons, that are the real players in chemistry. They're the ones on the front line, available to interact.
Got it. And the main idea today is what happens when atoms, well, change how many of those valence electrons they have, either giving them up or grabbing more.
Exactly. Because when that number changes, the balance with the positive protons in the nucleus gets thrown off. The atom isn't neutral anymore.
It becomes charged. Right. An ion.
Precisely, an ion. And that single change, gaining or losing an electron, it drives so much of what happens chemically.
Okay, let's tackle one side first. Losing electrons. What goes on when an atom actually sheds one or more of these valence electrons?
Well, electrons are negative. So if you lose negative charge, you're left with more positive protons compared to the electrons remaining.
Meaning the overall charge becomes positive.
Right. The atom turns into a positively charged ion. We call that a ionization.
And electrons don't just fall off, right? You need to pull them away from that positive nucleus. That takes energy.
It does. There's an energy cost. We call it ionization energy. It's the specific amount of energy needed to actually remove an electron from an atom.
Okay, let's use an example. Sodium, Na, is a common one.
Perfect example. Neutral sodium has 11 protons, 11 electrons, and critically, it's got just one electron sitting out there in its outermost shell.
So if sodium loses that one electron,
it becomes the sodium ion, Na. Still got 11 positive protons, but now only 10 negative electrons. That imbalance gives it a +1 charge.
All right, so the equation is just Na yields NaO plus an electron, EO.
Simple as that. Na, E, no plus E.
So who tends to do this? Which elements are likely to lose electrons and become these positive cations?
Generally speaking, it's the metals. Think of like the alkaline metals, sodium, potassium.
Group 1 on the periodic table.
Yeah, and the alkaline earth metals like magnesium, calcium in group 2, also many of the transition metals.
Why them specifically?
They typically have lower ionization energies. Their outer electrons just aren't held as tightly as in other elements. It's easier to pluck them off.
Is there a bigger reason why they'd want to lose them, though? A driving force.
Oh, definitely. It comes back to stability. Atoms often lose electrons to achieve a more stable arrangement of electrons, one that usually looks like the configuration of the nearest noble gas.
Ah, the noble gases. Neon, argon. They're super stable, right? Unreactive.
Exactly. They have full outer electron shells. So sodium, its electron setup ends in the 3 Sigus. If it loses that one electron,
Its outer configuration becomes like neons, which is really stable.
precisely, it achieves that stable noble gas configuration by emptying its valence shell.
Okay, so it loses electrons, gets a positive charge.
Yeah.
What are the other big changes when an element undergoes this process, what you called oxidation?
Well, besides the charge, the most striking change, I think, is the size. The radius of the atom actually gets smaller, sometimes significantly smaller.
Hang on, that feels a bit weird. You lose a tiny electron, but the whole thing shrinks. Why?
Good question. 2 main reasons. First, you still have the same number of positive protons in the nucleus, but now they're pulling on fewer negative electrons.
So each electron gets pulled in more strongly.
Kind of, yeah. The effective nuclear charge per electron goes up, pulling the whole electron cloud tighter. And second, sometimes, like with sodium losing its 3s electron, you actually lose an entire electron shell. The next shell down becomes the new outer boundary, and it's naturally smaller.
Wow. Do you have numbers for sodium?
Yeah, they're pretty dramatic.
Right.
A neutral sodium atom is around 186 picometers across, but the ion, it's only about 102 picometers.
That's almost half the size, just from losing one electron.
Huge difference. And you also mentioned stability increases, obviously, and reactivity changes.
Right. Sodium metal is famously reactive, even explosive with water.
But the sodium ion, NiO, is incredibly stable. It's what's in your table salt, essential for life. And as a positive ion, it's now looking for electrons. We say it becomes electrophilic, electron-loving.
And the name for this whole process, losing electrons.
It's called oxidation. We say the element that loses electrons has been oxidized.
Okay, oxidation. Losing electrons, becoming a positive excciation, shrinking.
Yeah.
Let's flip it. What about gaining electrons?
So gaining electrons means adding negative charge. Now you have more electrons than protons.
So the net charge becomes negative.
Exactly. It becomes a negatively charged ion, which we call an anion.
Is there an energy factor here too, like ionization energy for losing?
Yes, it's related. It's called electron affinity. This is the energy change when an atom gains an electron. For many atoms that like to gain electrons, energy is actually released, which makes the process favorable.
Okay, if sodium was our losing example, what's a good one for gaining?
Chlorine, Cl, is a classic, neutral chlorine. 17 protons, 17 electrons.
Needs one more electron to get a stable configuration, right?
Right, so if it gains one electron,
It becomes the chloride ion. Clay, still 17 protons, but now 18 electrons. Net charge, -1.
perfect. And the equation is Cl plus an electron yields clay. Cl plus E a clay.
So which elements are the typical electron gainers?
Mostly the nonmetals, especially the halogens, fluorine, chlorine, bromine. They're very good at grabbing an extra electron. Also elements like oxygen and sulfur.
And what makes them good at it?
They tend to have high electron affinities, meaning it's energetically favorable for them to gain an electron. And they also have high electronegativity. That's a measure of how strongly an atom pulls electrons towards itself in a chemical bond. They just have a strong attraction for electrons.
And their motivation is the same as the metals, just achieved differently. Stability.
Absolutely. Still chasing that stable, noble gas configuration. Chlorine, for example, its configuration ends in 373 Pu. It just needs one more electron to fill that Pu subshell and get to 373 Pu.
Which looks like argon. Stable.
Exactly. Filling the valence shell, often following the octet rule, aiming for 8 outer electrons.
Okay, so for gaining electrons, which we'll call reduction soon, what are the key changes? Negative ion and anion.
Right, an anion forms. The magnitude of the negative charge tells you how many electrons were gained. Oxygen usually gains 2, becoming O out.
In the size. You
Wow.
hinted it was dramatic here too.
Oh, yeah. But it goes the other way. When an atom gains electrons, its radius increases significantly.
Okay, now this raises a question too. Adding a tiny electron makes the whole ion swell up.
Mhm.
Why the expansion?
It seems odd, but think about the electrons already there. You're adding more negative charge into that electron cloud.
More negatives pushing each other apart.
Exactly. Increased electron repulsion. They repel each other, pushing the cloud outwards. Plus, the nucleus's positive pull is now spread over more electrons, so each one feels a slightly weaker pull on average, allowing them to spread out more.
Makes sense. Do we have numbers for chlorine?
We do. Chlorine atom, about 99 picometers. Chloride ion, kilo, swells up to about 181 picometers.
Wow, nearly doubles.
Huh.
So losing shrinks, gaining expands. Fascinating. And stability increases here too. Reactivity changes.
Definitely. Chlorine gas, COs, is reactive and toxic. The chloride ion, Clu, is stable, essential in your body, found in salts. And anions, being negative, are attracted to positive charges. They're nucleophilic and can act as electron donors in reactions.
And the name for this process, gaining electrons.
That's reduction. The element gaining electrons is said to be reduced.
Okay, so we have oxidation, losing electrons, getting positive, shrinking, and reduction, gaining electrons, getting negative, expanding. Why is understanding this trade-off so crucial?
Well, the key thing is, these two processes, oxidation and reduction, they almost never happen in isolation. They're two halves of a whole.
They happen together.
Always together. You can't have one without the other in a chemical reaction involving electron transfer.
And that leads to some major consequences, like forming ionic compounds.
Exactly. You form a positive commutation through oxidation, a negative anion through reduction. Opposite charges attract very strongly.
Electrostatic forces, like magnets.
Right. That strong attraction forms ionic bonds, holding the ions together in a crystal lattice structure. That's what ionic compounds, or salts, are, like sodium chloride, NaCl.
Table salt. And the properties are totally different, right?
Completely different. Reactive sodium metal plus toxic chlorine gas react, electrons transfer, and you get stable, edible sodium chloride salt. The compound bears little resemblance to the starting elements.
Amazing transformation. Okay, so that's one consequence. What's the other big one?
The broader concept of oxidation-reduction reactions, or redox reactions for short.
Redox. That term covers any reaction where electrons are transferred.
Precisely. And the core principle, again, is that oxidation, the loss, and reduction, the gain, happen simultaneously. Electrons move from one substance to another?
One thing loses, another thing gains those same electrons.
Yes. And we have terms for the roles they play. The substance that takes the electrons, causing the other guy to be oxidized, is called the oxidizing agent.
So the oxidizing agent gets reduced itself.
Exactly. And the substance that donates the electrons, causing the other guy to be reduced, is the reducing agent.
And the reducing agent gets oxidized itself. It's like a partner dance.
It is. And chemists use something called oxidation states or oxidation numbers as a kind of bookkeeping tool to track where the electrons are moving.
Right, you mentioned that. Losing electrons makes the oxidation state go up.
Like sodium going from 0 in the element to +1 in the ion, nior into nio.
And gaining electrons makes the oxidation state go down.
Like chlorine going from 0 in COU to -1 in the ion, chlon to Cli.
The numbers help us follow the electron flow. Okay, that makes sense. So just to quickly bring it all together, what are those key underlying factors again that decide who loses and who gains?
It really comes down to those inherent properties of the atoms. Low ionization energy makes it easy to lose, typical for metals.
High electron affinity makes it favorable to gain, typical for nonmetals.
Right. High electronegativity also means a strong pull for electrons, favoring gain, again, nonmetals.
And size matters too.
Yep. Larger atoms tend to lose electrons more easily because the outer ones are further from the nucleus and shielded. Smaller atoms can sometimes gain electrons more readily because the incoming electron can get closer to the positive nucleus.
And the ultimate goal driving all this.
That quest for stability, achieving a stable electron configuration, usually like a noble gas, the octet rule is a big part of that for many elements.
That desire for stability is really the engine here.
It truly is.
Okay, so wrapping up our deep dive. Losing electrons is oxidation. You form a positive cation, the radius shrinks significantly, and this is common for metals aiming for stability.
And gaining electrons is reduction. You form a negative anion, the radius expands significantly, common for nonmetals aiming for stability by filling their outer shell.
And critically, these happen together in redox reactions. This electron exchange is the basis for forming ionic compounds and drives countless chemical changes.
Understanding this give and take of electrons is just fundamental. It unlocks so much about bonding, reactivity, really how matter behaves.
Like the currency of chemistry in many ways.
Couldn't have said it better myself.
So as a final thought for you, the listener, to take away from this, think about how basic this electron trading is. Now look around you, the salt on your table, obviously, but also rust forming on iron. That's redox.
Oh yeah, classic oxidation.
Or how a battery works. That's literally controlling the flow of electrons released in a redox reaction to generate power.
Absolutely.
How many things in your everyday life are ultimately governed by these simple rules of atoms gaining and losing electrons? It's happening constantly, everywhere, just beneath the surface.
It really is chemistry in action, all around us.
Well, thanks for joining us on this deep dive into the fascinating world of electron transfer.